Now that we have kindergartners in the school, we're going to take you way back to kindergarten, grade 1 math here. Let me ask you a question here. What's 3 plus 4? Good. 3 plus 4 is equal to 7. At least according to the grade 1 way of adding, 3 plus 4 is equal to 7. That's correct, right? 3 plus 4 is equal to 7. That's what you learn in grade 1, and it's what it is. If you're adding scalars, but that's the only thing that you learned to add in grade 1 was scalars. Now, your grade 1 teacher probably didn't tell you you were adding scalars. Your grade 1 teacher may not have even realized you were adding scalars. In the end, your grade 1 teacher taught you how to add numbers, how to add positive integers, which are essentially scalars. When you got to grade 6, maybe, you learned to add vectors. So 3 plus 4 wasn't necessarily 7. 3 plus 4 could have equaled 7. 3 plus 4 could have equaled negative 7. 3 plus 4 could have equaled 1. Or 3 plus 4 could have equaled negative 1. If the 3 was in one direction and the 4 was in the same direction, 3 plus 4 was 7. But if the 3 was in one direction and the 4 was in the opposite direction, in other words, one was a positive and one was a negative, then they added together to give me 1 or negative 1. Does that make sense? You guys know how to do that now. Like, you guys are experts at adding vectors in one dimension, just the same as you are at adding scalars that you learn in grade 1. So we've got grade 1 math, nailed it. Grade 6 math, nailed it. Now it's time for grade 10, grade 11 math. Sometimes 3 plus 4 is equal to 7. Sometimes 3 plus 4 is equal to 1. Sometimes 3 plus 4 is equal to 5, or some other number entirely. If the 3 is in one direction and the 4 is perpendicular to that, when we add those together, we don't get 7 or 1, we get 5. So today we're going to learn to add those vectors in 2 dimensions. When we do that, the normal rules of vector addition, the rules that we learned in grade 1, and then the somewhat more complicated rules of vector addition in 1 dimension that we learned in grade 6, they don't apply anymore. 3 plus 4 doesn't necessarily equal 7. 3 plus 4 could equal some other number. So how do we figure out what it is? Well, to do addition in 2 dimensions, we got to start drawing pictures. So even though we're doing grade 10, grade 11 math, we've got to go back to grade 1 in the way we solve things, draw pictures. To add 2 numbers together, we're going to draw a picture. The goal, every time we're solving one of these vector addition problems, every single time, the goal is to get what we call a vector diagram that is a right-angled triangle. So something like this. That's a right-angled triangle. Or something like this. That's a right-angled triangle. We don't want a triangle that looks like this. It's a triangle, but it's not a right-angled triangle. The goal is to get a vector diagram, and I'll explain what that means in a second, that is a right-angled triangle. And then, once we have this or this, we use a little bit of trigonometry, which you definitely learned in grade 10, I think it was. Let's talk about the vector diagrams themselves. We know we need a triangle. We know what that is. But what's a vector diagram? Vector diagram is a diagram that shows the addition of different vectors. We first have to draw each vector. Each vector is going to be drawn as a line segment with an arrow showing direction. So if I asked you to draw a vector showing 10 meters to the east, you would draw a line segment with an arrow on the end of it showing 10 meters to the east. If I asked you to show a vector, or draw a vector showing 25 meters per second to the south, then I would draw a vector, a line segment with an arrow on the end of it pointing south, and label it 25 meters per second. Five meters to the west, 10 meters per second to the north, and so on. We don't have a vector diagram drawn yet, but at least we know how to draw the vectors. A vector is a line segment with a little arrow on the end of it indicating direction. Now, how do we connect these together to add them? How do we connect these together into a vector diagram, a right-angled triangle vector diagram, so that we can add them up with some trigonometry? Well, the vector diagram has my vectors that I want to add drawn front to back. What do I mean by that? This is the front of a vector. This is the back of a vector. Sometimes we call it the head and tail, the front and back. If I'm adding two vectors together, let's say I'm adding 3 meters to the east, and I'm adding 4 meters to the north. Then I would draw 3 meters to the east, and I would draw front to back 4 meters to the north. Do you see how these two vectors are drawn front of one vector to the back of the next vector? Can't draw it like this, because they're drawn back to back. Can't draw it like this, even though the vectors are drawn in the right direction, they're drawn front to front. This is the one that I've got to do, because they're drawn front to back, or head to tail. There is another option here, by the way. There is one more option. I asked you guys at the beginning of this lesson, what's 3 plus 4? You guys said 7. I could have said, what's 4 plus 3? What would the answer be, according to the grade 1 way of adding? 7. Doesn't matter what order we add things in, right? So we're adding scalars in 2 different orders, we get the same number. Add vectors in 2 different orders, we get the same number as well. 3 plus 4 is equal to whatever. We could also say 4 plus 3 is equal to whatever. Does that meet the criterion here? Is it drawn front to back? The front of one vector to the back of the next? Sure it is. Either one of those works out. So the goal is to get a right angle triangle. We're close. How do we get a right angle triangle? Well, we have to draw vectors. Vectors are line segments that have an arrow on the end of it showing direction. Then with those arrows, with those vectors, we have to put them together. And we put them together in a particular way, not just any random way. We've got to put them together front to back. So the front of one vector matches up with the back of the next vector. Then we got to connect those two. Call it the resultant vector, from start to finish. There's my resultant vector. It goes from the start of the 3 to the finish of the 4. Or, if you're doing it over here, it would go from the start of the 4 to the finish of the 3. There's a little typo here, actually. This should say from start to finish. So notice that resultant vector, that red vector, isn't drawn front to back at all. It's drawn back to back and front to front, from start to finish. If I can find the value of that red vector, that is the sum of the vectors. Just like in grade 1, when you learned 3 plus 4 is equal to 7. Okay, 7 was the sum of those scalars. Now, that red vector is the sum of the vectors 3 plus 4. How do you think we might find that value of r? Yeah? Pythagorean theorem, right? This is grade 9 or grade 10. Pythagorean theorem. We would say r, in both cases here, we would say r is equal to this, let's take that back a step here. A squared plus b squared is equal to c squared. Well, c is the value of r there, right? So we're going to say r is equal to a squared plus b squared, or r is equal to the square root of 3 squared plus 4 squared. And when you do that, You get 5. This is how 3 plus 4 can equal 5 when you're adding vectors. So picture this. Picture this. I told you on day 1 or day 2 of Physics 20, when day 1 I think it was actually, when you're finding a displacement, you can add displacements together. I walk 3 meters to the north. I walk 4 meters to the north. I walk 1 meter to the south. Add them all up. 3 plus 4 plus -1 gives me 6. Well, now I'm saying we're going to add vectors in 2 dimensions. We still add them, but we have to add them differently. 3 meters to the east, 4 meters to the north. What's my displacement now? 5 meters in a certain direction. We'll deal with that direction later on. Make some sense? So we're learning to add in a different way, and there's a reason, because sometimes things don't happen nicely in one dimension. Sometimes you're running around the track as opposed to just straight along the straightaway on the track, right? Sometimes you switch directions. Goal, get a right angle triangle, which we've done right here. How do we get that? Draw vectors, line segments with arrows on the end of them, then draw a vector diagram with the vectors drawn front to back. And then, of course, our resultant vector, R, that we're looking for, is drawn from start to finish. All right, we're going to add a few vectors here together as examples. The first one here, 10 meters to the north and 20 meters to the north. We know how to do this, right? This is easy. This is grade 6 math. 10 meters to the north, 20 meters to the north. It's all in the same dimension, so we don't have to draw a picture of this. We just say 10 plus 10, if we define north as positive. 10 plus 10 is equal to 20 meters. 20 meters to the north. Ten plus 20, I should say. Is equal to 30 meters. Okay, let's take a look at the second one here. 10 meters north, 20 meters south. A little bit harder, but we're just going to say, because it's one dimension here again, 10 meters plus negative 20 meters gives me negative 10 meters. Or we could say 10 meters to the south. Right? This is nothing new. First 2 questions, nothing new. This one, however, the third one, this one's different. Here we have 10 meters to the north and 20 meters to the east. Here we have 2 dimensions. The north-south axis, the east-west axis. Here we have to draw a picture. Remember, the goal of this picture is to get a right-angled triangle that is a vector diagram. So let's draw our vectors first of all. We got 10 meters to the north. And we have 20 meters to the east. I'm going to draw the 20 meters to the east about twice as long as the 10 meters to the north. Those are my vectors. Now, how do I put those together in a vector diagram? Well, I could go 10 meters and 20 meters like this, or I could have went 20 meters and then 10 meters like this. Either one of those are okay, because they both show these vectors drawn front to back. Never front to front, never back to back, always front to back. My resultant vector, by the way, would be this line right here that's drawn from start to finish. And I can find the value of that resultant vector. In both cases, it's going to be the same value. R is the square root of 10 squared plus 20 squared. It's the Pythagorean theorem, right? (22 meters). Now, there is a direction. It's important to have a direction because we're talking about vectors, but we'll deal with that later on. Okay, for now, we just want to find the magnitude of the sum of these vectors. 10 plus 20 equals 22 if we're adding them in these directions. What about the next one? 10 meters to the west, 20 meters to the south. Well, our vectors would look like this. 10 meters to the west, 20 meters to the south. I could draw that like this, 10 and 20. Or I could draw it like this, 20 and 10. Doesn't really matter because they both show the same thing. Notice in both cases, vectors are drawn front to back. My resultant vector, start to finish. In both cases, the Pythagorean theorem says that r would be equal to the square root of 10 squared plus 20 squared, which works out to be exactly the same value as it did in the last question, right? 10 plus 20 north and east, 10 plus 20 west and south. They gave me 22 meters in both cases. The direction is different, but again, we'll deal with that direction later on. Good? All right, those went okay. Let's deal with something slightly more complicated. I asked you what 3 plus 4 was at the beginning of this lesson, and you said 7. Good. If you're adding scalars, it is equal to 7. Then we learned that 3 plus 4 was equal to 5 sometimes. What's 3 plus 4 plus 6? Sorry, what's 3 plus 4 plus 5, I mean? Adding scalars, 3 plus 4 plus 5 is equal to 12, right? What's 3 plus 4 plus 5 equal to when you're adding vectors in 2 dimensions? That's a problem. Remember the goal, what's the goal? Always get a right-angled triangle. How do you get a triangle when you're adding 3 vectors together? We got to use components. What do we mean by that? Well, I'll show you. I want to add 25 meters to the north plus 20 meters to the east plus 30 meters to the north. You could add those together if they were all to the north. That would be easy, right? 25 plus 20 plus 30 would be equal to 75 meters if they were all to the north. But when we're in 2 dimensions, we can't do that. When we're in 2 dimensions, we got to get a right-angled triangle that is a vector diagram. But how do we get a triangle with 4 sides? You can't. So we got to break it into components. What do we mean by that? Watch carefully. I'm going to break it into what I call X and Y components. Everything on this axis, in other words, east-west, is X. Everything on this axis is north-south. So the first vector, 25 meters to the north, has nothing on the x-axis. 25 meters to the north is all y-axis. It's all upwards. So let's write that in here. Now, 20 meters to the east is all x-axis. How much of this 20 meters to the east is y-axis? None. It's all x. Look, it's all on this axis. 30 meters to the north, well, that's all y-axis. So 0. None of it is x-axis. 30 meters is y-axis. Now I've got 0 plus 20 plus 0 is 20. 25 plus 0 plus 30 is 55 meters. Now I can add up 20 and 55 in 2 dimensions. So now I can go over here and say 20 meters to the east on the x-axis, 55 meters to the north on the y-axis. Remember, front to back still. And then my resultant vector, the sum of those vectors, is going to be drawn from start to finish. Remember, the goal, always get a vector diagram that is a right-angled triangle. I couldn't do that when I had 3 numbers to add together, so I had to simplify it into 2 numbers. To simplify it into 2 numbers, I combined components. 0 plus 20 plus 0, 25 plus 0 plus 30. Now I can redraw it as a simple right-angled triangle vector diagram. And now I can find the value of r pretty easily, right? R is equal to the square root of 20 squared plus 55 squared. Let's do that one on a calculator just to make sure we're on the right track with that. We're going to say 20 squared plus 55 squared Let's square root that. 58.5 or 59. So 25 plus 20 plus 30 in this case ends up equaling 59 meters. At an angle with a direction, right, that we're going to deal with later on. Is that okay? Yep. No, you shouldn't always run to the nearest meter, but what we're doing here is going significant figures. In both cases, or in all three cases here, it's 2 significant figures. So our final answer should be 2 significant figures still. Let's try one more example, okay, and then we'll set you free to do a little bit more work. Oh my goodness, this one's 4 vectors. That's okay. We can deal with that now, right? We can deal with pretty much anything now. 10 meters to the east, 15 meters to the south, 12 meters to the west, 20 meters to the south. You can't just say 10 plus 15 plus 12 plus 20 equals, what is that, 25, 37, 57, because that would be adding scalars, and that's a grade 1 thing. Sometimes it's a grade 11 thing, but not in this case. And because there's more than 2 vectors, we got to break it into components, x and y, so that we can get ultimately our goal, which is a right angle triangle. So let's do that. How much of this 10 meters to the east is on the x-axis? How much of that 10 meters is on the x-axis? Look, if it's going to the east, how much of it is on the x-axis, Rosie? 10, all of it. How much of that 10 meters to the east, look at my hand, how much of this 10 meters to the east, right here, is on the y-axis? How much of it's up and down? How much of this is up and down? 0. All right, so go with the second vector, 15 meters to the south. How much of this 15 meters to the south is on the x-axis? North-south, right? How much of that is x? No. No. No, on the x-axis we're dealing with it. Right. 0 on the x-axis. How much of it's on the y-axis? Yeah, we're going to make it negative 15 because it's to the south. Good. Right, if it's on this plane, it's x. If it's on this plane, it's y. Next one, 12 meters to the west. How much of that is x component? 12 meters to the west, negative 12, because it's west, right? And none of it is on the y-axis. 20 meters to the south, none of it's on the x-axis. Negative 20 is on the y-axis. Negative because it's south. Okay, let's add them up. 10 plus negative 12 is negative 2 meters. Negative 15 plus negative 20 is negative 35. Now I can redraw this so that I have a simple right angle triangle that's a vector diagram. 2 meters to the left, negative 2. 35 meters down, negative 35. Drawn, what do we got? Front to back. Resultant vector, start to finish. By the way, lots of people ask me, do I need to put the negative in here? Do I need to put the negative in right here? No. You need to show direction. The negative shows direction over here. The arrows show direction here. When you're plugging into the Pythagorean theorem, you never need to put a negative in. Never. Add those together, I still end up getting 35 to 2 digits, right? Because 35 plus 2 is equal to 35 at some angle some direction that we'll talk about later on. Okay? Let's take a look now at the next two questions on your worksheet, questions 4 and 5, please, on that worksheet. All right. If you guys are okay with those, let's move forward a little bit further still. What if we're trying to find the sum of vectors, but they're not at 90 degrees to each other? It's not 10 meters to the north and then 20 meters to the east. What if they're at some kind of funny angle? By a funny angle, I mean something other than 90 degrees. We've still got to find components like we did in the last set of examples that we did. But this time the components are a fair bit more difficult. Let's just quickly work through these ones again. These ones are easy because these ones aren't crazy angles, funny angles. Okay, we got 10 meters. Okay, the x component would be 10 meters. The y component would be 0. Here, the x component would be 0. The y component would be 200. Here, the x component would be negative 50. The y component would be 0. And here, the x component would be 0, and the y component would be negative 35. Those are easy, right? Those are easy. But what if one of those vectors was at a funny angle, other than 90 degrees? It wasn't straight on the x-axis or straight on the y-axis. What would we do then? How would we find the x and y components of those? For example, listen, we have 100 meters here. We're not adding things together yet, right? We just got a funny angled vector. We know how to add vectors if they're not funny angles. So let's learn how to deal with the funny angle, kind of get rid of that, and then add it as some other vector. How do you find the x and y components of these vectors? Here's what I want you to do. Draw a triangle. Triangles are big here. This is not your vector diagram triangle. This is not your final goal. Remember, the final goal was to get a right-angled vector diagram triangle. Okay? This is only one step along the way. Draw a triangle. Draw a triangle such that the angle is inside that triangle. Okay, that means that we don't want to draw a triangle like this because the angle isn't inside the triangle. Right? Draw a triangle such that the angle is inside. Label the one on the x-axis x. Label the one on the y-axis y. And then use some trigonometry. Oh my goodness. This is the one that people hate, right? Trigonometry. You guys remember SOHCAHTOA? Sorry? The easiest one? Oh, good, because that's what you got to use. SOHCAHTOA. Sine theta is equal to opposite over hypotenuse. Cosine theta is equal to adjacent over hypotenuse. And tan theta is equal to opposite over adjacent. Take a look at this first triangle over here. The x side of this triangle is the adjacent side. We have the hypotenuse. So let's say cosine 30 degrees is equal to adjacent over hypotenuse. Let's say sine 30 degrees is equal to opposite over hypotenuse. X, by the way, ends up being equal to 86.6, and y ends up being equal to 50. So we haven't added anything here, but we have found the x component of that vector and the y component of that vector. Look, back here, the x component was 10, the y component was 0. Up here, the x component is 86.6, and the y component is 50. It's weird to think of the x component as being a decimal number like that. All we're saying is that, look, of this 100 meters, 86.6 of it is along this axis, and 50 of it is along that axis. What about the next one? Well, this is at a funny angle as well. So let's resolve it. Let's label this x. Let's label this y. Let's say sine 30 degrees is equal to opposite over hypotenuse. The opposite is x this time. Let's say cos 30 degrees is equal to adjacent over hypotenuse, the adjacent side over the hypotenuse. Y ends up being equal to 17.32, I think. So, once again, the x component of this first vector was 10 meters. The y component was 0. The x component of this one is 10 meters. The y component is 17.32. Or, actually, that would be negative 17.32, right? Because it's downwards. All right, everybody, we'll have a look at your worksheet again. I want you to do questions 6 through 13 on your worksheet now. 6 through 13. All right, now we want to deal with adding vectors with funny angles. So we've added scalars. We've added vectors in one dimension. We've added vectors in 2 dimensions when there was only 2 vectors. We've added vectors in 2 dimensions when there was 3 or 4 or 5 vectors. We found vector components of funny angled vectors. Now we're going to add vectors together that are at funny angles, including ones where we have 3, 4, 5 vectors. So for instance, let's say we got a problem like this. Guy walks 10 meters to the east, then he walks 5 meters to the south, and then he walks 30 meters, 30 degrees right here. We want to add these vectors together. If we're adding them as scalars, the distance traveled, 10 plus 5 plus 30 is equal to 45. But if we want to find the displacement, add the vectors together, how do we do it? Well, I'll tell you what. The first thing that I want you to do whenever you see a funny angle like this, 30 degrees, is get rid of it. Break it down into components like you just did on the questions you were working on. Okay, repeat after me, these 5 words. Okay, these 5 words I want you to say every single time you see a funny angle. You're not doing a very good job of repeating. I don't like funny angles. I don't like funny angles, so get rid of it. Let's get rid of this funny angle here. All right, we'll pick this up tomorrow. Bottom line is we get rid of the funny angle like we just did, and then we combine the components like we did before. But again, we'll pick this up tomorrow.